Welcome. In these notes, a vector is more than a number. It is an arrow with both magnitude and direction, and it obeys the parallelogram law when vectors are added. Velocity, acceleration, momentum, force, electric field, and torque are common vector quantities. Current can have magnitude and direction in everyday language, but in this course it is treated as a scalar because it does not follow vector addition. Several labels describe special arrows. Equal vectors have the same magnitude and direction. A null vector has zero magnitude because its initial and terminal points coincide. A unit vector has magnitude 1, so the unit vector along A is A divided by the magnitude of A. The reciprocal vector keeps A's direction but has reciprocal magnitude, and the negative vector keeps the magnitude while reversing direction. In 3 dimensions, every vector is resolved into perpendicular components. A equals A sub xi plus A sub zk. Its magnitude is the square root of A sub x squared plus A sub y squared plus A sub z squared. Dividing by that magnitude produces the unit vector. Think of this as the first machine. An arrow enters, and its length and direction are separated into readable components. The dot product is the machine that measures alignment. Given vectors A and B with angle theta between them, A dot B equals the magnitude of A times the magnitude of B times cosine theta. Because cosine is positive for an acute angle, 0 for a right angle, and negative for an obtuse angle, the sign of a dot product tells us the angle type. In components, if A is a sub x, A sub y, A sub z, and B is B sub x, B sub y, B sub z, then A dot B equals A sub x, B sub x, plus A sub y, B sub y, plus A sub z. The basis vectors make this work. I dot I, J dot J, and K dot K are 1, while different basis vectors have dot product 0. The dot product is commutative, so A dot B equals B dot A. It also gives projection. The scalar projection of A onto B is A dot the unit vector along B. Let's verify the note's parameter example. A is 2 times squared, 4 times 1, and B is 7 minus 2x. Their dot product is 14 times squared minus 8 times plus x, which is 14 times squared minus 7 times, or 7 times 2 times minus 1. For an obtuse angle, this must be negative. The sign chart gives x positive with 2 times minus 1 negative, so 0 is less than x is less than 1/2. The other sign combination is impossible. The answer is therefore 0 less than x less than 1/2. The next machine acts on fields. For a scalar field phi of x, y, and z, the gradient is nabla phi, equal to partial phi over partial x in the I direction, plus partial phi over partial y in the j direction, plus partial phi over partial z in the k direction. Geometrically, the gradient points normal to a level surface, where phi has constant value, and its magnitude is the maximum rate of increase. A unit normal is the gradient divided by its magnitude. The directional derivative in a unit direction u is the dot product of the gradient with u. For the notes, example 9. Let f be x squared y cubed minus y to the 4th. Its gradient is 2xy cubed, 3 times squared y squared minus 4y cubed. At 2, 1, this becomes 412 minus 4, or 48 if using the written derivative directly. However, the supplied booklet's worked line uses the first component as 2xy cubed and evaluates it as 4, while its stated final value 6 square root of 2 corresponds to the gradient. 4, 4. We should follow the booklet's stated worked result for the lesson. With direction 1, 1 over square root of 2, the displayed directional derivative is 6 square root of 2. Divergence is a scalar. Partial v sub x over partial x plus partial v sub y over partial y plus partial v sub z over partial z. Positive divergence indicates a source, negative divergence a sink, and zero divergence a solenoidal field. Curl is a vector obtained from the determinant with I, j, k, and the field components. It measures local rotation. Zero curl means an irrotational field, often expressible as the gradient of a potential. A level surface also gives equations for tangent planes and normals. Suppose phi of x, y, z equals a constant, and P is the point with position vector r. The gradient at P is normal to the tangent plane. If r is any point of the tangent plane, then r minus r lies in the plane and its dot product with the gradient is 0. In components, this becomes x minus x times phi sub x, plus y minus y times phi sub y, plus z minus z times phi sub z, equal to 0. A point on the normal instead travels parallel to the gradient, so the cross product of r minus r with the gradient is 0. The notes sphere example uses x squared plus y squared plus z squared equals 6 at p equal to 2, 1, 1. The gradient is 2 times 2y 2z, so at p it is 4, 2, 2, and the unit normal is 2, 1, 1, divided by square root of 6. This is the outward direction. For a fluid field, curl tells us whether the motion rotates. In example 15, the velocity components are y sine z minus sine x sine z plus 2yz, and xy cosine z plus y squared. Computing the three curl components gives 0 because the matching partial derivatives cancel pair by pair. Therefore, the motion is irrotational, and there is a potential phi with gradient equal to the velocity. Integrating the first component with respect to x gives xy sine z plus cosine x. Matching the y and z components adds y squared z. The velocity potential is phi equals xy sine z plus cosine x plus a constant. The important pattern is consistent. Gradients point normal to levels. Divergence measures source strength, and curl detects rotation. A line integral measures how much of a vector field points along a path. At a point on a curve, the unit tangent is dr over ds, so the tangential component of f is f dot dr over ds. Multiplying by ds gives f dot dr, and integrating from a to b gives the line integral. When f is a force, this is work. When the field is a fluid velocity and the path is closed, the closed line integral is circulation. For a conservative field f equal to gradient phi, the integral from p to q is the change phi at q minus phi at p, independent of path. Around a closed path, it is 0. Let's work the notes example 16. The field is f equal to 5xy minus 6 times squared, I plus 2y minus 4 times j, and the curve is y equal to x cubed from 1, 1 to 2, 8. Along the curve, write y as x cubed and dr as d by I plus 3 times squared, dxj. Substitute into f. Its first component becomes 5 times to the fourth, minus 6 times squared, and its second becomes 2 times cubed, minus 4 times. Dotting with dr gives 5 times to the fourth, minus 6 times squared, plus 3 times squared, times 2 times cubed, minus 4 times, which simplifies to 6 times to the fifth plus 5 times to the fourth, minus 12 times cubed, minus 6 times squared. Integrating from 1 to 2 gives 35, as recorded in the notes. The path is not decoration. It determines dr and therefore determines the work unless the field is conservative. A surface integral measures the component of a vector field crossing a surface. If n is the unit normal, the local normal component is a dot n, and the flux is the double integral of a dot n ds. Orientation matters. Reversing n reverses the flux. If a surface is not parallel to a coordinate plane, project it onto a convenient plane. For projection onto the xy plane, the surface element contributes d by dy divided by the absolute value of n dot k. Similar formulas use dy dz with n dot I, or d by dz with n dot j. This compensates for the angle between the surface and its projection. Consider the note's first octant sphere example with f equal to yzi plus zxj plus xyk and x squared plus y squared plus z squared equal to 1. The outward unit normal is xyz because the gradient is 2 times 2y 2z and the surface radius is 1. The dot product f dot n is xyz plus xyz plus xyz, or 3xyz. On the upper spherical patch, projection onto the xy plane introduces division by z, leaving 3xyz d by dy. In polar coordinates, on the quarter disk, x is r cosine theta, y is r sine theta, and d by dy is r dr d theta. Thus, the flux is 3 times the integral of r cubed cosine theta sine theta, with r from 0 to 1 and theta from 0 to pi over 2. The radial integral is 1/4, and the angular integral is 1/2, giving 3 over 8. The workflow is always normal: projection, substitution, limits, and evaluation. A volume integral adds a scalar or vector quantity throughout a three-dimensional region. The basic form is the triple integral over v of a dv. The main skill is describing the region with correct limits. In cylindrical coordinates, dv is rho, d rho, d phi dz. In spherical coordinates, it is r squared sine theta dr d theta d phi. The notes example 27 integrates t equal to xyz squared over a prism. The base is the triangular region in the first quadrant bounded by x plus y equal to 1, with z from 0 to 3. Therefore, y runs from 0 to 1, x runs from 0 to 1 minus y, and z runs from 0 to 3. Integrate x first. The integral from 0 to 1 minus y of x dx is 1/2 times 1 minus y squared. The remaining y integral is 1/2 times the integral from 0 to 1 of y times 1 minus y squared dy, and the z integral of z squared from 0 to 3 is 9. The y integral equals 1/12, so the final value is 1/2 times 9 times 1/12, or 3/8. The notes also give a volume example for the first octant portion of the cylinder x squared plus y squared equal to 4 between z equal to 0 and z equal to 3 times. The region has x from 0 to 2, y from 0 to the square root of 4 minus x squared, and z from 0 to 3 times. Integrating this volume gives 8. Notice how the bounds carry the geometry. The curved boundary controls y, while the sloping plane controls z. The vector-related theorems are conversion machines. The divergence theorem applies to a closed surface and converts outward flux into a volume integral. The surface integral of A dot ds equals the volume integral of divergence A dv. Stokes's theorem applies to an open surface with a closed boundary and converts the circulation around that boundary into the surface integral of curl A through the surface. The boundary orientation must agree with the right-hand rule. Green's theorem is the planar version. For a positively oriented closed curve, the integral of m dx plus n dy equals the double integral of partial n with respect to x minus partial m with respect to y. In the notes example 29, v is r squared times the position vector r inside a sphere of radius a. Its divergence is 5r squared. Using spherical volume element, the flux becomes 5 times the integral of r to the 4th from 0 to a times the theta integral of sine theta times the phi integral. These evaluate to a to the 5th over 5, 2, and 2 pi, producing 4 pi a to the 5th. Example 30 illustrates Stokes on the upper unit hemisphere. Its boundary is the unit circle in the xy plane, so set x equal to cosine theta, y equal to sine theta, and z equal to 0. The line integral reduces to the integral of 2x minus y times dx, which evaluates to pi. For Green's theorem, the notes region between y equal to x squared and y equal to x gives the integral of x minus 2y over the region, producing negative 1/20. Choose the theorem by the geometry. Closed surface means divergence, open surface with boundary means Stokes, and planar closed region means Green. Let's verify the divergence theorem in the notes unit cube example. The field is A equal to y squared I plus 2xy plus z squared j plus 2yzk, and the cube is 0 less than or equal to x, y, z less than or equal to 1. First, compute the divergence. The x derivative of y squared is 0. The y derivative of 2xy plus z squared is 2 times. The z derivative of 2y's is 2y. Therefore, divergence A is 2 times plus 2y. Integrating over the unit cube gives 2 times the integral of x plus y. The x contribution is 1/2, the y contribution is 1/2, and the z length is 1, so the volume integral is 2. Now calculate flux face by face. On the face x equal to 0, the outward x component contributes 0. On the opposite x face, the y squared component integrates to 1/3. Depending on the face labels and orientation in the booklet, the paired x face contributions are 1/3 and -1/3, so they cancel. For the y faces, the face at y equal to 1 contributes the integral of 2 times plus z squared, while the opposite face contributes the corresponding negative expression. The notes record the pair as 4/3 and -1/3 after their face parametrization. The z face contributions are 1 and 0. Adding the listed face values gives 1/3 minus 1/3 plus 4/3 minus 1/3 plus 1 plus 0, which equals 2. Thus, the surface flux agrees with the volume integral, verifying the theorem. The key lesson is not memorizing 6 unrelated integrals. It is recognizing that divergence measures the net outward flow accumulated inside the cube. We finish with linear dependence, which connects determinants and geometry. 3 vectors u, v, and w are linearly dependent if there are scalars alpha1, alpha2, and alpha3, not all 0, such that alpha1 u plus alpha2 v plus alpha3 w equals the 0 vector. In that case, at least one vector can be built from the others, so the 3 vectors do not form a basis for 3-dimensional space. They are linearly independent when the only solution is alpha1 equals alpha2 equals alpha3 equals 0. Independent vectors point in genuinely different directions and can represent every vector in 3-dimensional space through a unique linear combination. The scalar triple product gives a fast geometric test for 3 vectors. If the determinant of their component matrix is 0, they are coplanar and therefore linearly dependent. This connects directly to our central example. For A, B, and C, the determinant became 8 mean minus 52. At m equal to 13/2, the determinant is 0. The parallelepiped collapses into a plane, and the vectors are dependent. For any other value of m, the determinant is non-zero, the volume is non-zero, and the 3 vectors are independent. Across the chapter, the same arrow machine idea keeps returning. Dot products measure alignment and projection. Cross products create normal directions and areas. Scalar triple products measure signed volume and coplanarity. Gradients point toward maximum increase, divergence measures source strength, and curl measures rotation. Line, surface, and volume integrals accumulate field effects along curves, across surfaces, and through regions. Finally, the divergence, Stokes, and Green theorems convert one kind of accumulation into another. If you can identify the geometry first, the notation becomes a reliable set of instructions. Here is the complete checklist. Start with the geometry. For 2 vectors and an angle, use the dot product to measure alignment, projection, or perpendicularity. For a normal direction or parallelogram area, use the cross product and its determinant. For 3 vectors, use the scalar triple product. Its absolute value is parallelepiped volume, and 0 means coplanarity or linear dependence. In our main example, A was 1 minus 1 minus 2, B was 3, 5, 6, C was -1, 4, m, and the determinant reduced to 8m minus 52. Setting it to 0 gave m equal to 13/2, with C landing at -1, 4, 13/2. For fields, the gradient gives the direction of greatest increase and a normal to level surfaces. Divergence measures net outward flow, while curl measures local rotation. Line integrals accumulate tangential effect, surface integrals measure flux, and volume integrals accumulate through a region. Use spherical coordinates for spheres and radial geometry, and cylindrical coordinates for cylinders and circular symmetry. Finally, choose divergence for closed surfaces, Stokes for open surfaces with a boundary, and Green for planar closed regions. The recurring habit is simple. Identify what is being measured, Choose the matching machine, write its geometric limits, and verify the final number.